On June 19th, 2020, an instrument on board a spacecraft 11 billion miles from Earth began picking up something it was never specifically built to detect. A faint, steady radio emission, vibrating at a frequency of 3.11 kilohertz, arriving from somewhere in the emptiness beyond our solar system. NASA scientists confirmed it. This was a real signal, captured by real instruments coming from a region of space no working spacecraft had ever measured this closely before. We are talking about Voyager 2, humanity's only fully functioning spacecraft, actively sending back data from true interstellar space, and the story of the strange, persistent frequency its instruments picked up shortly after crossing the true boundary of our solar system. Before you get too excited, let's be clear about something important right from the start. This is not a signal from an alien civilization. What it actually is turns out to be almost as fascinating once you understand what NASA scientists discovered. It actually represents. Stick around, because this story reveals something genuinely strange about the mostly empty space between the stars. Let's set the stage properly first, because context matters enormously here. Voyager 2 launched in August of 1977, eventually becoming the only spacecraft in history to fly past all 4 giant planets in our solar system: Jupiter, Saturn, Uranus, and Neptune. After completing that historic tour, it kept traveling outward, and on November 5th, 2018, it officially crossed the heliopause, the invisible boundary where the constant outward pressure of our sun's solar wind finally gives way to the vast, cold ocean of interstellar space. That crossing made Voyager 2 only the second human-made object in history to leave the protective bubble surrounding our entire solar system, following its twin spacecraft, Voyager 1, which had made the same crossing back in 2012. Here is what makes Voyager 2 uniquely valuable for this particular discovery. Voyager 1's plasma wave instrument, the exact tool needed to measure charge, particles, and radio emissions in the surrounding space, had actually stopped functioning correctly decades before that spacecraft ever reached interstellar space. Voyager 2's equivalent instrument, however, remained fully operational, giving scientists their first real, continuously functioning set of eyes and ears on what interstellar space actually sounds like, in the most literal sense that phrase can be used. Quick pause here. If you find this kind of real, verified, deep space discovery genuinely fascinating, go ahead and tap that like button. Right now it costs you nothing, and it really does help this channel keep making videos exactly like this one. So what exactly did Voyager 2 detect? Beginning on that day in June of 2020, at a distance of roughly 124.2 astronomical units from the Sun, meaning over 124 times farther from the Sun than Earth is, Voyager 2's plasma wave science instrument began registering radio emissions, quickly followed by something called Electron plasma oscillations, appearing clearly within its 3.11 kilohertz spectrum analyzer channel. In simpler terms, the spacecraft's instruments detected charged particles in the surrounding interstellar plasma vibrating together at a specific, measurable frequency, creating a signal researchers could actually analyze and interpret. That frequency turned out to be scientifically valuable in a very specific way. The exact pitch of a plasma oscillation is directly tied to the density of electrons in the surrounding space, meaning scientists could use this single detected frequency to calculate roughly how many electrons exist within a given volume of interstellar space near the spacecraft. Using Voyager 2's readings, researchers calculated an electron density of approximately 0.12 electrons per cubic centimeter, with some additional supporting evidence pointing toward a slightly lower estimate of around 0.087 electrons per cubic centimeter. Either way, this represented a real, measured data point about the density of matter existing in the space between stars, gathered directly rather than estimated indirectly from a distance. If you are new here and love stories about real scientific discovery, the kind grounded entirely in actual verified data, now would be a great time to hit that subscribe button, because there is a lot more of this waiting for you. This discovery actually matched something researchers had already confirmed with Voyager 2's twin. When Voyager 1 crossed into interstellar space back in 2012, its own plasma wave instrument detected similar oscillations, first in October and November of that year, and again in April and May of 2013, each event triggered by a coronal mass ejection, a powerful burst of solar activity that had traveled outward from the Sun and eventually reached the spacecraft, sometimes taking well over a year to arrive from the moment it first erupted off the Sun's surface. Scientists at the time compared the effect to plucking a guitar string, describing how a solar shockwave passing through the thin interstellar plasma effectively strums the charged particles into a brief, detectable vibration, a phenomenon researchers nicknamed the sounds of interstellar space. What made Voyager 2's June 2020 detection particularly interesting was its timing and duration. Unlike some of the earlier, brief plasma oscillation events triggered by specific solar storms passing through, This signal appeared to persist for an extended period, giving researchers an unusually long, steady window to study the surrounding interstellar plasma in detail. Separate research and Voyager 1's data around this same general period found something similarly persistent, a very weak narrowband plasma wave emission that continued showing up from 2017 onward, allowing scientists to track subtle, small-scale fluctuations in interstellar plasma density over time, essentially giving researchers their first steady, continuous measurement of turbulence occurring in the space between the stars. Researchers studying this data, including scientists at Cornell University and the University of Iowa, have proposed a few different possible explanations for exactly why this persistent signal exists. One leading idea suggests the emission may come from thermally excited plasma oscillations, essentially a background hum caused by the natural thermal energy present in the surrounding interstellar gas, constantly nudging charged particles into subtle vibration, even without a dramatic triggering event like a solar storm. A closely related explanation points to something called quasi-thermal noise, a very specific, understood type of electrical signal generated whenever individual electrons pass close to a spacecraft's antenna, creating tiny detectable pulses that, when averaged together over long periods of observation, reveal a consistent underlying frequency tied directly to the surrounding plasma density. It is worth being completely clear about something here, because this detail matters enormously for understanding the story accurately. This detected frequency is not a radio broadcast in any meaningful communicative sense. It is not a message, a transmission, or anything resembling an intentional signal sent by anyone or anything. It is a natural physical phenomenon, the electromagnetic signature created whenever charged particles in a very thin, very cold plasma vibrate together in response to their surrounding environment. NASA scientists have been completely transparent about this from the very beginning, describing these detections purely in terms of plasma physics rather than anything resembling communication or technology. That said, the scientific value of this discovery is genuinely significant on its own terms, without needing any dramatic reinterpretation. Before Voyager 2 provided this kind of continuous, functioning data, scientists had a limited, patchy understanding of conditions immediately beyond our solar system's protective bubble. Every additional measurement of electron density, every subtle fluctuation tracked over time, helps researchers build a far more accurate model of what the true edge of our solar system and the interstellar space immediately surrounding it actually looks like at a detailed physical level, information that was previously based mostly on theoretical prediction rather than direct real-time measurement. This data also plays directly into a much larger ongoing scientific question. The heliosphere, the protective bubble of solar, wind, and magnetic fields surrounding our entire solar system, shields Earth and everything on it from a significant portion of the harmful cosmic radiation constantly drifting through the galaxy. Understanding exactly how dense, how turbulent, and how variable the interstellar plasma is immediately outside that bubble helps scientists build better models of how effectively that shield actually works, and how it might change over time as our solar system continues its slow orbit around the center of the Milky Way galaxy. Both Voyager spacecraft continue facing a very real, ongoing challenge as they gather this kind of data. Their power sources, radioactive generators that have been steadily decaying since launch back in the 1970s, produce noticeably less usable electricity every single year. NASA engineers have already been forced to permanently shut down several onboard instruments, simply to keep both spacecraft transmitting at all. And current estimates suggest both Voyagers likely have only a handful of years of meaningful operational life left before their remaining power finally drops too low to keep any instruments running. Every additional data point these two spacecraft managed to send back, genuinely precious. Nobody currently has any active mission plan that will reach true interstellar space again for decades, meaning whatever electron density measurements, plasma oscillation frequencies, and turbulence patterns. Voyager 1 and Voyager 2, managed to record before finally going silent, will likely remain the only direct in situ data humanity has from this region of space for a very long time to come. That makes the modest engineering team still operating both spacecraft today something close to caretakers of an irreplaceable scientific archive, carefully rationing power and prioritizing instruments to squeeze out every last useful measurement before time and distance finally catch up with these two extraordinary machines. It also helps to understand exactly how an instrument built using 1970s technology is even capable of detecting something this subtle in the first place. Voyager 2's Plasma Wave Science instrument uses two long antennas arranged in a V-shape on the spacecraft, originally designed to study conditions around the giant planets during the mission's primary tour of the solar system, decades ago. Nobody involved in building that instrument back in the 1970s could have possibly anticipated it would still be functioning nearly 50 years later, quietly measuring the electromagnetic hum of interstellar plasma from a region of space that, at the time, existed only as theoretical speculation. The instrument works by capturing extremely faint voltage fluctuations picked up by those antennas, then converting that raw data into a frequency spectrum that scientists back on Earth can study for telltale patterns. Exactly the kind of pattern that revealed this 3.1 kilohertz signal in 2020. Detecting a signal this faint requires an enormous amount of patience and careful signal processing as well. Researchers studying this kind of data often need to average measurements together over long stretches of time, sometimes separated by an entire week between individual data points, specifically because the signal itself is so weak that shorter observation windows simply cannot pick it up reliably. This is very different from how scientists typically study plasma waves closer to home, where dramatically stronger signals from the solar wind can be measured accurately using observation windows lasting only a few seconds. Interstellar space, by comparison, is remarkably quiet and stable, which paradoxically makes its faint signals both harder to detect and, once found, far more scientifically valuable since they represent a much more constant, reliable baseline measurement of conditions in that region. That relative quietness is itself an important scientific finding. Inside the heliosphere, conditions are constantly disturbed by solar activity, changing rapidly and unpredictably as bursts of energy from the sun ripple outward through the solar system. Once Voyager 2 crossed into true interstellar space, researchers noticed something different. The plasma density and electromagnetic conditions surrounding the spacecraft became noticeably more stable and consistent over time, compared to the constantly fluctuating environment found closer to the sun. This distinction alone offers researchers a valuable point of comparison, helping them understand exactly how dramatically different conditions are on either side of the heliopause boundary, information that is nearly impossible to gather using any method other than direct in situ measurement from a spacecraft that has actually made the crossing itself. Scientists have also used these detections to cross-check earlier theoretical predictions about the density of interstellar space, predictions that had been made using indirect methods long before either Voyager spacecraft actually reached the boundary. Before these direct measurements were available, researchers estimated that plasma density in the outer heliosphere sat somewhere around 0.002 electrons per cubic centimeter, with a substantial jump expected once a spacecraft crossed fully into interstellar space, potentially increasing anywhere from 20 to 50 times higher. The actual measurements gathered by both Voyager spacecraft confirmed this general prediction was correct, while also providing scientists with far more precise, real-world numbers to work with going forward, refining decades-old theoretical models using genuine physical data gathered directly from the region in question. So the next time you see a headline claiming NASA detected a mysterious frequency from beyond our solar system, know that the real story, while less dramatic than an alien transmission, is genuinely remarkable in its own right. A 50-year-old spacecraft, built using 1970s engineering, managed to detect the faint, natural hum of charged particles vibrating in the emptiness between the stars, giving scientists real, measurable data about a region of space that had previously existed only in theoretical models and educated guesses. If this story left you appreciating just how much real science is still being discovered by these incredible, aging spacecraft, make sure you are subscribed with notifications turned on, because Voyager 2 is still out there right now, still listening, and still transmitting, and there is a very good chance. The next signal it sends back reveals something else about interstellar space that nobody has ever measured directly before. Somewhere, out past the edge of our solar system, a machine older than most of the scientists studying its data is still quietly humming along, gathering measurements from a region of the galaxy that, until just a few years ago, existed only in theory, tracked by a small, dedicated team back on Earth who refused to let it go silent a moment sooner than absolutely necessary. One carefully rationed watt of power, and one faint, precious signal at a time, still teaching us something new about the galaxy nearly 5 decades after it first left home. And that alone might be one of the most remarkable achievements in the entire history of space exploration, a fitting final chapter for two machines that were only ever expected to last a few short years past the outer planets.